Okay. So in this chapter, chapter 9, we want to discuss how to estimate population parameters. So a population parameter like a proportion or a mean or a standard deviation based on a sample statistic. Like the idea that we explored pretty in a lot of depth in chapter 8 was that these things are random variables. Their values are going to change pretty drastically. Well, maybe not super drastically, but they're going to change from one sample to the next. So, so if we have a particular, sample proportion, we want to know, well, what does that say about the population proportion? Like, what can we say about the population proportion based on the sample proportion? So some terminology to get us started. The sample proportion p hat is sometimes called a point estimate for the population proportion p. Excuse me. Now, as I just finished saying, right, different samples are going to result in different point estimates. So we can't estimate p to any degree of certainty just by using a point estimate p hat. Instead, what we're going to do is report a range of values called a confidence interval to estimate p. And we can adjust that interval so that we're as certain as we wish to be that the interval contains the true population proportion. How certain we are is called the level of confidence. And there's a give and take between how certain we are and how good the information is, okay? And I'll talk about that as we look at an example. But I just want to kind of cut to the chase. I'm going to do kind of the same thing that I did in chapter 8 and just give you the result. And then we'll talk about how we arrive at this result. We'll talk about what Statcrunch is doing behind the scenes a little bit later on in this section. But for now, I just want to show you how to get the interval, and then I'll talk. Then later on, we'll talk about what Statcrunch is doing, what calculations it's performing. So if we want to construct a confidence interval for the proportion, we go to stat. Proportion stats, one sample, and then either with data or with summary, depending on if we have the raw data or just a summary of it. So for example, this first one says the drug Lipitor is meant to lower cholesterol levels. In a clinical trial of 863 patients who received 10 milligram doses of Lipitor daily, 47 reported headache as a side effect. Okay. Now, part A says compute a point estimate for the proportion of Lipitor users who will report headache as a side effect. Well, the point estimate for the proportion is p hat, right? P hat is just the number of successes, like the number of people who have the characteristic in question, divided by the total number of people. In this case, there were 863 people in total, and 47 of them reported headache. So p hat would be 47 out of 863. So 47 out of 863 is about 0.054. So about 5.4% of people in this study experienced headache as a side effect. And there's our point estimate. And that's all there is to part A. Now part B says construct and interpret a 90% confidence interval for the proportion of Lipitor users who will report a headache as a side effect. So this 90% thing, this is our confidence level. This is how confident we want to be that our interval actually contains the population proportion. So to get that, we go stat, proportion stats, one sample, with summary. Because we don't have the raw data, we have a summary. When we get there, we're going to be prompted to enter the number of successes and the number of observations, right? So the number of successes in this case was 47. The number of observations was 863. And we also want to enter our confidence level, which we said was going to be 90%. So let's go to Statcrunch and see what this looks like. So we go stat, proportion stats, one sample with summary. And then you come to a screen that looks like this, where again, you're prompted for the number of successes, the number of observations, right? Number of successes we said was 47. Number of observations we said was 863. And I'm going to click on the confidence interval button, not the hypothesis test. We'll talk about hypothesis tests in chapter 10. But for now, I want to do the confidence, construct a confidence interval. And I want the confidence level to be 90%. So I'm going to change this to 0.9. Okay, leave the method on standard walled, right? Don't change that. And then you hit compute. So in this table, they give us several important things. One of the things they give us is the sample proportion right there, which is what we got when we did part A by hand, you know, about 5.4%. So that's p hat, right? This thing is p hat. But our interval is given by these two numbers right here. L limit stands for lower limit, U limit stands for upper limit. So this is our lower limit and our upper limit, or our lower bound and our upper bound, whatever you want to call them. And what these things mean is that the true population proportion is somewhere between 0.04 and let's say 0.042 and 0.067. Right? So the true population proportion is somewhere within that range of numbers. Okay, and that's what that means. So I'm going to write that down. 0.042, 0.067. When I write this down, I'm using interval notation here, right? So it almost looks like an ordered pair or something, like when you were plotting points back in algebra class. It almost looks like that, but on the left-hand side goes your lower bound, and on the right-hand side goes your upper bound. They always go that way. Don't put the bigger number here, put the smaller number here and the bigger number there, okay? But that's it. There's our confidence interval, right? So we've used Statcrunch to construct our confidence interval. Now we're also supposed to interpret the confidence interval. So what is the interpretation of this? Well, our confidence level was 90%, right? So what this means is we are 90% certain that the true population proportion is somewhere between 4.2% and 6.7%, okay? So in other words, based on our sample proportion of 5.4%, we're 90% sure that the true population proportion would be somewhere between 4.2% and 6.7%. Okay, so I'm going to write that down. We're 90% sure that the true population proportion of Lipitor users who experience headache as a side effect So we're 90% sure that the true population proportion of Lipitor users who experience headache as a side effect is somewhere between 0.042 and 0.067. Or if you like percentages, you could say that it's somewhere between 4.2% and 6.7%. Okay? So there's the interpretation. And I want to contrast that with part A, right? In part A, the sample proportion was 5.4%. But if I were to ask you something like, how confident are you that the true population proportion is exactly equal to 5.4%? Your answer should be 0, right? We are not sure at all that this is the true population proportion. But we can be 90% sure that it's somewhere between 4.2% and 6.7%, okay? So hopefully that makes some sense. Let's look at the next task in this problem. So the next task says, construct and interpret a 99% confidence interval for the proportion of Lipitor users who will report a headache as a side effect. And just for the sake of argument, I'm going to remind us that the 90% confidence interval, so the 90% confidence interval was 0.042 to 0.067. Okay, so now what we want to do is construct and interpret a 99% confidence interval. So we're going to do the same thing, right? We're going to go stat, proportion stats, one sample with summary. We're going to enter the same stats as before, right? Number of successes was, I think, 47. Number of observations was 863. This time, though, we want a confidence level of 99%. So that's really the only thing that changes. So let's go to Statcrunch and see how that affects our interval. So I'm actually going to leave this one up here so we can compare stuff, but we go stat, proportion stats, one sample with summary. We had 47 successes out of 863 observations, and this time we want a 99% confidence level, confidence interval. Okay, so these are the results. You'll notice that the sample proportions are the same, right? They're the same. Of course they are, right? Because the sample proportion is just number of successes over number of observations, and those counts are the same as they are, or those counts are the same in both problems, right? The standard error is also the same. Standard error that refers to the standard deviation of the sample proportion, right? But that didn't change either. What did change is our upper and lower bounds, our confidence interval itself. Notice that the interval got wider when we moved up in confidence. That should make some sense to you. We'll talk about it in a second. Let's just write down the results though. So 0.035 approximately to 0.074 approximately. Okay, so there's our confidence interval. Now, so we've constructed it, now let's interpret it. So the interpretation is the true population proportion is, we'll say, let me start over. So we'll say we're 99% sure the true population proportion is between 0.035 and 0.074. Okay, so in part B, when we constructed the 90% confidence interval, we said, well, we're 90% sure that the true population proportion is somewhere between 4.2% and 6.7%. But if we wanted to be more certain that our interval actually contains the true population proportion, well, then we need a wider interval, right? We need a wider interval, okay? And so while we're only 90% sure that the true population proportion falls somewhere between here and here, we can be 99% sure that it falls somewhere between 0.035 and 0.074, right? Now, you can play around in Statcrunch a little bit, and Statcrunch won't let you compute a 100% confidence interval. There are mathematical reasons for that. But we can think about a 100% confidence interval. So this one says, without using Statcrunch, construct and interpret a 100% confidence interval for the proportion of Lipitor users who will report a headache as a side effect. So now think about it. If we want to be 100% certain that our interval contains the true population proportion, then we could just say that the proportion is somewhere between 0 and 1. Right? We're 100% sure that the true population proportion is somewhere between 0% and 100%, right? It has to be. And that's the interpretation, right? So there's our interval. The interpretation, we're 100% sure the true population proportion is somewhere between 0% and 100%, right? So, so yeah, you can be as certain as you want to be that your proportion actually contains the true population proportion. The trouble is that the more certain you want to be, the less good information you get. Like here, this is completely useless, right? Sure, yeah, you know, we're 100% certain that the population proportion is somewhere in here, but that information is pointless. It's like, of course, the population proportion is somewhere between 0% and 100%, right? It doesn't give you any meaningful information. So that's sort of the dance that you have to perform. It's like the more certain you want to be, the larger your interval gets, and the larger your interval gets, the less the less illustrative the interval is, right? Like it doesn't tell you anything, it doesn't give you any good information. So that's kind of the balancing act you have to perform. Now we'll talk a little bit more about these confidence levels and stuff, and how that plays out when you're trying to perform inference. There are times when you're okay being only 90% confident. There are other times when you really do want to be 99% confident, right? More often than not, the confidence level that we use is 95%. So most of the time we will use a 95% confidence level, but it could be any confidence level you want, really. Anyway, let me walk you through another example. So this one says, in July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. Part A says to construct a 95% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. Go ahead and give the video a pause and see if you can do that on your own. Okay, so here's what we're going to do. Same as before. Stat, proportion stats, one sample with summary. We're going to have to enter the number of successes. In this case, there were 1,783 people polled, and 1,123 of them said yes, right? They were in favor. So number of successes is 1,123. Number of observations was 1,783. And the confidence level that we're working with is 95%, right? It says construct a 95% confidence interval. Okay, so let's do that, see what we get. Okay, the confidence level is already at 95%, so I don't need to change that. And then I hit compute, and this is what we get, right? So I'm going to write that down. I typically round these to 3 decimal places, but you know, you could round them to whatever. 60.7, 65.2. Okay, and that's it. We weren't asked to interpret this interval, we were just asked to construct it. So there you go, I've constructed it. I'll give you a verbal interpretation. So just verbally, I mean, we're 95% sure that the true population proportion of people in favor of the death penalty is somewhere between 60.7% and 65.2%, right? We're 95% sure it's somewhere between these numbers. Okay, so then we can answer a bunch of questions. Like part B says, is it possible that 61% of registered voters are in favor of the death penalty? Is it likely? Yeah, it's possible. It's possible. Is it likely? Well, 61% is within this interval, right? 61% is between 60.7% and 65.2%. So I'd say, yeah. Is it likely? So yes, it's possible. And yes, it's likely. Because it's within the confidence interval. Okay, part C. What about 75%, right? Is that possible / likely? 75%? Well, it's possible, right? It's definitely possible because we're only 95% sure that the true population proportion is within these numbers. That means there's a 5% chance that it's some number outside of this interval. 75% is possible then, right? It is possible. Now, is it likely? No, not very, right? It's not very likely. There's only a 5% chance that the true population proportion is outside of this interval. So while it is possible that 75% is the true population proportion, it's not very likely that that's the case, okay? So yes, it's possible. But no, it's not likely. Right? Because 75% is outside the confidence interval. Okay? So yeah, 75% is possible. Is it likely? No, it's not likely. Part D, what about 102%? Is that possible / likely? Well, no, it's not possible, right? So no, it's not possible. And if it's not possible, then it's definitely not likely. It can't even happen. It's not possible, right? No, it's not possible. It's not possible. So of course it can't be likely because it's not even possible. You can't have more than 100% of something, right? So it's not possible that 102% of people are in favor of the death penalty. Like, what would that even mean, right? Like, at most, 100% of people can be in favor of the death penalty. So no, this is not possible. Okay, so hopefully that helps make sense of these confidence intervals. So we've seen some interpretations and we've seen some like asking of questions about these things. And hopefully at this point you're really kind of catching on to the whole point here. So with that in mind, then, you're ready, I think, at this point to probably tackle most of the homework problems. So if you're one of those students with a really short attention span, then you could stop the video here and try to tackle the homework problems. And if you get stuck, maybe come back and watch a little bit more or something like that. But what I want to do now is discuss what it is that Statcrunch is doing behind the scenes, right? Because I don't want you to walk away from this class with the feeling that everything we did was just magic and that it's just guesswork, because it's not guesswork. We're not saying that we think there's like, we're not using subjective probabilities here, right? We're not saying, oh yeah, there's a 90% chance, but it's like just a guess that, you know, the proportion is in here. It's like, no, we're exactly 90% sure that the true population proportion is in the interval that we're giving, right? So we can verify this. It's mathematically rigorous, and I want to try to convince you of that. Okay. So here's what Statcrunch is doing. First of all, note that the center of all the confidence intervals we've computed has been the point estimate p hat. Right? We really saw that pretty clearly in the first example. Okay. Because our point estimate on this first example was 5.4%. When we constructed our 90% confidence interval, 5.4% is right in the middle of this interval. When we constructed our 99% confidence interval, again, 5.4% is right in the middle of this interval. Okay, so our point estimate is always right in the middle. Here, our point estimate, we didn't actually compute it, but we could do that real quick, right? 1123 out of 1783 is 62 point, well, almost 63%. And sure enough, right, 63% is right in the middle of this interval. So yeah, the center of the confidence intervals, the number that's kind of right in the middle, has been the point estimate p hat. So what Statcrunch is doing to compute the confidence interval is something like this. It's computing a point estimate, and then it's adding and subtracting the same amount from that point estimate. So to get the upper bound, it adds a little bit, and to get the lower bound, it subtracts that same amount. Okay? The amount that they're adding or subtracting is called the margin of error. Okay, so suppose that a confidence, for example, suppose that a confidence interval for the proportion of unicorns with rainbow mane is 0.23 plus or minus 0.04. What's the point estimate? What's the margin of error? What's the width of the interval? And maybe I would say, what is the interval itself? So we'll do that as well. But point estimate, the point estimate is this number right here, right? 0.23. Unicorns, rainbow mane. Oh my goodness, what am I doing? But there's the point estimate. Margin of error is this number right here. It's the thing that we're adding and subtracting, 0.04. And then what is the width of the interval? So the width of the interval, well, let's see what the interval itself would be, right? So 0.23 plus or minus 0.04. We can actually do that math, right? We can say 0.23 minus 0.04, right? So there's our lower bound. So our lower bound is 0.19. And then 0.23 plus 0.04, 0.27, that's our upper bound. Okay, so this is our confidence interval. Now, what is the width of that confidence interval? Well, it's just the difference between the upper bound and the lower bound. So we'll say the width of the interval is 0.27 minus 0.19, and that comes out to 0.08. What you may notice is that the width of the interval is twice the margin of error, right? So margin of error times 2 gives you the width of the interval, all right? Let me give you another example. This one's maybe a little more challenging. It says, suppose that a confidence interval for the proportion of unicorns with pink mane is 0.137 to 0.185. Okay? So the true population proportion of unicorns with pink mane is somewhere between 13.7% and 18.5%. Now, what is the point estimate? What's the margin of error? And what's the width of the interval? So the point estimate should be the number that's right in the middle of this interval. Okay, so to find that, we could use the midpoint formula, right? So we could say it's, you know, this plus that divided by 2. Okay, so 0.137 plus 0.185 divided by 2. If you're thinking midpoint formula, where in the world do we talk about that? We didn't talk about that in this class. I'm just expecting that you kind of know that from your algebra days. If you don't know it, don't worry too much about it. Don't stress out. Okay, but the point is that the point estimate here would be 0.161. That's the number that's right in between these two. Okay, so that's the point estimate that must have been used in the construction of this interval. So we're kind of working backwards on this one a little bit, right? But yeah, this is the point estimate that must have been used for the construction of this interval. What's the margin of error? Well, a couple ways you could get the margin of error. One way to do it is that since you know that this is your midpoint, then you could say the margin of error is the distance from the midpoint to the upper bound, or it's the midpoint to the lower bound. That distance should be the same since this number is right in the middle, okay? So you could just say, you know, 0.185 minus 0.161. That's one way you could do it. Another way you could do it, though, is you could say, well, the margin of error is going to be the width of the interval divided by 2, right? So you could say, well, it's 0.185 minus 0.137 divided by 2. Right? Doing 0.185 minus 0.137 gives you the width of the interval. The margin of error is going to be half of that, right? So that's 0.024. Okay, there's the margin of error. Now, we could verify that our work here is correct because remember, our interval should be of the form point estimate plus or minus margin of error. So if the point estimate is 0.161 and the margin of error is 0.024, then we can say the lower bound would be 0.161 minus 0.024, which sure enough is 0.137. And the upper bound should be 0.161 plus 0.024, which is 0.185, sure enough, right? There's our upper bound. So yeah, that makes me feel good. It makes me feel like we've got the right idea here. What's the width of the interval? Well, the width is just twice the margin of error, right? It's the difference between this and that. So the width of the interval would be 0.185 minus 0.137. That's 0.048. Okay, so there's that. So anyway, the moral of the story is Statcrunch is going to do point estimate plus or minus margin of error. Now the point estimate, we already know how Statcrunch computes that. It's the number of successes divided by the number of observations. But the margin of error, how does Statcrunch compute that part of the formula? How does it get the margin of error? Another way to ask that question is, how do we determine the margin of error necessary for us to be as certain as we wish to be? So, for example, if I want to be 95% certain that my confidence interval contains the population proportion parameter, how big does the margin of error need to be? So to answer that question, we need to introduce some notation, okay? So first of all, the level of confidence we've already talked about, right? The level of confidence of a confidence interval is how certain we are that the interval contains the true population proportion. The level of significance is the complement of the level of confidence, and it's denoted by alpha, okay? So for example, for a 95% level of confidence, alpha would be 0.05. We always express alpha as a decimal instead of a percentage, okay? But it's 0.05 because 100% minus 95% is 5%, and we just express it as a decimal, right? So to give you another example, for a 97% level of confidence, alpha would be 0.03 because 100% minus 97% is 3%, okay? This number is called the level of significance, right? So level of confidence and level of significance, they're complements of each other. So now here's the notation that we need. Z sub k denotes the z-score whose area to the right is k. All right. So you could use the normal calculator to figure out what z sub, let's say you wanted to figure out z sub 0.03, right? You would use the normal calculator, change it so that the area is going to the right, and then then fill in the area to be 0.03, and the z-score that corresponds to that area is z sub 0.03, right? That's how that works. Now for a 1 minus alpha times 100% confidence interval, so for like a 95% confidence interval, right, alpha would be 0.05. For that level of confidence, z sub alpha over 2 is called the critical value. Okay, so z sub alpha over 2 is called the critical value. With that notation in mind, now I'm going to give you the formula that Statcrunch uses to compute confidence intervals. Okay, so this is the formula that Statcrunch uses. So provided that these conditions are met, n times p hat times q hat needs to be bigger than or equal to 10, and little n needs to be less than or equal to 0.05 times capital N. If that's true, then a 1 minus alpha times 100% confidence interval is point estimate p hat plus or minus margin of error, z sub alpha over 2, right, our critical value, times sigma sub p hat, right, our standard deviation. And just to remind you, right, sigma sub p hat is the square root of p hat times q hat divided by n. And q hat is just 1 minus p hat, right? It's the probability of failure. So I want to prove to you that this formula really is what does the trick, right? This will really give us, like for a 95% confidence interval, then then here we would have p hat plus or minus z sub 0.025 times sigma sub p hat, right? This really does the trick. Here's why. So here's a proof. So first of all, recall that if these conditions are met, then p hat is normally distributed. We talked about that in chapter 8, right? So if these conditions are met, then p hat is normally distributed, and the mean u sub p hat is equal to the proportion p. And the standard deviation, sigma sub p hat, is equal to the square root of p hat q hat over n. Okay, so far so good. Next, note that 1 minus alpha times 100% of the observations fall within z sub alpha over 2 standard deviations of the mean. I realize that that's very abstract. It's kind of hard to wrap your brain around. So let me try to make it easier, right? So by giving you a concrete example. So for example, 95% of the observations will fall within z sub 0.05 divided by 2, right? If our confidence level is 90%, then alpha is 0.05. 0.05 divided by 2 is 0.025. And if you go to the normal calculator and you find out what this z-score is, you would see that this is about 1.96. Okay, so note that 95% of observations are going to fall within 1.96 standard deviations of the mean, right? That would be a concrete example. But more generally, 1 minus alpha times 100% of the observations are going to fall within z sub alpha over 2 standard deviations of the mean, more generally speaking. So here's a picture of what's going on, right? We know that p hat is normally distributed, so we've got this normal curve. And we know that 1 minus alpha times 100% of the sample proportions are going to fall within z sub alpha over 2 standard deviations of the mean. So this is p minus z sub alpha over 2 times the standard deviation, and this is p plus z sub alpha over 2 times the standard deviation, right? So here we are z sub alpha over 2 standard deviations below the mean, and here we are z sub alpha over 2 standard deviations above the mean, okay? So using our concrete example, we know that 95%, if we were using our concrete example, we would know that 95% of the sample proportions are between p minus 1.96 times the standard deviation and p plus 1.96 times the standard deviation, okay? So we can be exactly 1 minus alpha times 100% sure that p hat is somewhere between these two values. In other words, we could set up this inequality, right? P hat is somewhere between p minus z sub alpha over 2 times sigma sub p hat and p plus z sub alpha over 2 times sigma sub p hat. What we want to figure out is what interval is p in, right? So here we have an interval in which p hat lies. We want to get an interval in which p lies. So we could do that. We just need to solve for p. So what I'm going to do is subtract p. So I'm going to subtract p in every location here. Right, so those cancel. I get negative z sub alpha over 2 times sigma sub p hat is less than p hat minus p is less than, those cancel, z sub alpha over 2 times sigma sub p hat. then I need to get p by itself, so I'm going to subtract p hat through now. So I'm going to say, minus p hat, minus p hat, minus p hat, and we get negative p hat minus z sub alpha over 2 times sigma sub p hat is less than negative p, which is less than negative p hat plus z sub alpha over 2 times sigma sub p hat. And then finally, we'll divide through by -1. So if we divide this thing through by -1, remember that when you divide an inequality by a negative, the signs flip. So if we divide through by -1, we get positive p hat plus z sub alpha over 2 times sigma sub p hat is greater than positive p, which is greater than positive p hat minus z sub alpha over 2 times sigma sub p hat. In other words, p is somewhere between p hat minus z sub alpha over 2 times sigma sub p hat and p hat plus z sub alpha over 2 times sigma sub p hat. So we are exactly 1 minus alpha times 100% sure that p is somewhere between those values, right? Therefore, a 1 minus alpha times 100% confidence interval for p is p hat plus or minus z sub alpha over 2 times sigma sub p hat, just like we set up here. Now, if you didn't follow all of that, don't worry, I'm not going to test you on it, okay? I included it, like I said, I included it because I don't want you to think that this is just magic or that it's just a guess. It's not a guess, it's mathematically rigorous. We are exactly, 1 minus alpha times 100% sure that our population proportion is going to fall within this interval. Okay, we can be, it's a very mathematically precise thing. If you want to understand it, then rewatch the video. If the video is not good enough, you could look stuff up online, you could read the textbook. But yeah, so hopefully that convinces you that this really is a mathematically rigorous thing. I'll give you an example where we do one by hand. So this one says, same scenario as example 2. I don't know why I called this example 5. I think we're only on example 3. Probably. Oh no, it is example 5. No, okay, it is example 5. It says, same scenario as example 2. A Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder, and 1,023 were in favor, right? So we've seen this scenario before in example 2. Now, part A asks us to verify that the requirements for constructing a confidence interval for P are satisfied. Okay, that's something that we haven't done yet, and it's important. You're going to be asked to do that in the homework. The requirements are these. Okay, those are the requirements that they're asking us to verify. So, so requirement number 1, n times p hat times q hat needs to be bigger than or equal to 10. Let's see if that's true. We've verified these requirements before, right, when we were doing the chapter 8 stuff, but let's just remind ourselves, right? So n is 1,783. P hat would be x over n, so that's 1,123 divided by 1,783. That's p hat. And then q hat is 1 minus p hat. I'm just going to do that in my calculator real quick. Right? Q hat is 1 minus p hat. 1 minus 1123 out of 1,783. So 660 out of 1,783. And I want to know if this is bigger than or equal to 10. Pretty sure it is. We could cross cancel a little bit to make our calculations a little easier. So I'm going to do 1123 times 660 divided by 1,783. Yeah, that comes out to 415.7-ish. So it's about 415.7, but I mean, it's way bigger than 10, right? So that first condition is met. The second condition that we have to check is that little n has to be less than or equal to 0.05 times capital N. This one is more difficult to test because we weren't told what the population size is. However, we're talking about United States registered voters. I don't know off the top of my head how many registered voters there are. I know that there are like almost 300 million Americans, or maybe there's more than that now, I don't know. But there's around 300 million Americans. So how many of us are registered voters? Well, probably at least 2/3 are registered voters. But either way, I mean, I think even if we're playing this on the safe side, we could say like 1 million. Like we could say our population size is, sorry, 100 million, right? So what we're trying to test to see is 1,783 less than or equal to 5% of 100 million? And I mean, it's pretty safe to say that that's true, right? So 5% of 100 million, well, 1% of 100 million would still be like, what is that? 1 million, 1 million, right? So 5% of 100 million is 5 million. And 1783 is definitely less than or equal to 5 million, right? So that condition holds. All right, so those conditions hold up. I'll be honest with you. On tests and quizzes, I'm not going to ask you to do this because it's kind of a time-consuming thing to have to check the conditions, and I'm more interested in your ability to construct the interval and interpret the interval, okay? But on the homework, you will be asked to check conditions often, okay? And when they ask you to check conditions, this is what they're asking you to do. So now part B, it says, by hand, construct a 95% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. Compare your answer here with what you got for example 2. Ooh, okay. So the formula, if we're going to do this by hand, the formula is p hat plus or minus z sub alpha over 2 times sigma sub p hat. Sigma sub p hat is square root of p hat times q hat over n. Okay. So first things first, maybe let's figure out what p hat is, right? Before I can use this formula, I need to do some scratch work. So p hat is going to be 1123 out of 1783. That's about 0.630. If we round it to 3 decimal places, is about 0.630. So I need p hat, I've got it. I need q hat. Well, q hat is just 1 minus p hat. So 1 minus 0.63 is 0.37. So q hat is about 0.37. I need n. N is given in the problem, right? N was 1783. That's our sample size. The last thing that I need, though, is this z sub alpha over 2 business. Z sub alpha over 2. Now, you'll never need to do this as far as I know. I don't think you'll ever have to do this, but let me just show you where you could get the z sub alpha over 2. So if we want a 95% confidence interval, then that would mean alpha is 0.05, right? So z sub alpha over 2 in this case would be z sub 0.05 over 2. And 0.05 divided by 2 is 0.025. So we're looking for z sub 0.025. What that means is that we're going to use the normal calculator, and we want the area to the right to be 0.025. So I'm going to go to the normal calculator. And we want to change the area to be 0.025. We want the area to go to the right, okay? And so then it shades in that critical region, and there's the critical value, right? So rounding to 2 decimal places, we would call this 1.96, right? Okay, so this is approximately 1.96. So now we have all the pieces we need. We can plug them into the formula. So we can say, all right, our confidence interval is going to be 0.630 plus or minus z sub alpha over 2 times the square root of p hat times q hat divided by n. Okay, so that's 0.630 plus or minus 1.96 times the square root of 0.63 times 0.37 divided by 1783. 0.022 approximately. And so now what we would do is take turns subtracting this number from that number and then adding this number to that number. So if we subtract, we get 0.63 minus 0.022. That's 0.608. And then if we add, we get 0.63 plus 0.022. And that gives us 0.652. So there's our confidence interval. Okay? It says compare your answer here with what we got when we did this in Statcrunch in example 2. Well, when we did this in Statcrunch, we got 0.607 and 0.652. So really close. Not quite the same. We're off by a little bit. The reason that we're off is because we did rounding here, we did rounding here, we did rounding here, and all of these rounding errors are starting to compound and they're starting to affect our answers, which is why you should just use Statcrunch. Just use Statcrunch. You're welcome to use Statcrunch on any of the problems on tests and quizzes and on the homework. Just use Statcrunch. It's going to be more accurate. It's going to give you a more accurate answer. Okay? But now you know what Statcrunch is doing. This is what Statcrunch is doing. It's just that it's a machine and it can do it a lot faster and with a lot fewer mistakes than we can. So, so just use Statcrunch is the moral of the story. But hopefully now you have a greater appreciation for what Statcrunch is doing, and hopefully you're somewhat convinced that it's not just magic. It really is math. It's just that you're not doing a lot of the computations. Your job is to interpret what Statcrunch spits out, right? The interpretation here is we're 95% sure that the true population proportion of people who are in favor of the death penalty is somewhere between 60.8% and 65.2%. Okay, so that's that. Now there is one last topic that we need to cover in this section, and it has to do with computing the sample sizes that you need in order to make these kinds of estimations, okay? So recall that the margin of error is z sub alpha over 2 times sigma sub p hat, or in other words, right, sigma sub p hat is square root of p hat times q hat over n. So it's this thing. Now, as the confidence level increases, the margin of error has to increase with it in order to, so that you can be more confident that your interval actually contains the true population parameter, right? But as the sample size increases, notice that as the sample size increases, as this denominator gets huge, the overall number is going to get smaller. So as your sample size increases, the margin of error decreases. So when it comes to sample sizes and margins of error and confidence levels and all of that stuff, there's just a lot of moving parts. But we can exploit that to figure out how large our sample size needs to be before we go out and collect data, right? We can figure out how much data we need to obtain in order for us to be as certain as we wish to be. So, so what we do is we set this thing equal to E for margin of error, right? So we let E equal this thing, and then we solve for the sample size, N, right? So solving for the sample size would require us to like divide by Z sub alpha over 2, and then square both sides, right? And then multiply by N and divide by the leftovers. Anyway, if you do all of that, here's the result that you end up with. So if you do all that, then you see that The sample size required to obtain a 1 minus alpha times 100% confidence interval for P with some margin of error E is given by this formula right here. We always round this up to the next integer, right? So we always round it up. We don't round it off, we round it up. So if you get n is approximately, 103.004, you're still going to round that up to 104, right? You always round up to the next integer. We can do this in Statcrunch as well. Okay, so I'm not even going to show you any of these calculations by hand, but you're welcome to do them by hand if you want to verify that what Statcrunch is doing is correct or whatever. But this is what Statcrunch is going to be doing behind the scenes. Now, to get Statcrunch to do it for you, you just go to Stat, Proportion Stats, one sample, and then go to Power/sample size. And once you do that, then you're going to click on the Confidence Interval Width tab and enter the stats that you're given, right? You want to make sure to leave the sample size blank because that's what you want Statcrunch to fill in for you. And remember that the width, the interval width, is twice the margin of error. So whatever they tell you in the problem is the margin of error, double that when you put it in for the width. So let me take you through a couple examples of this, and then we'll finally be done with this section. Kind of a long one today. Anyway, it says a sociologist wishes to determine the percentage of Americans who favor affirmative action programs for women and minorities for admission to colleges and universities. What sample size should be obtained if she wishes the estimate to be within 4 percentage points with 90% confidence if she uses a 2003 estimate of 55%, or if she does not use any prior estimate? So let's do part A first. We're going to go to Stat, Proportion Stats, one sample, and then Power/sample size. Okay, so let's go there to see what it looks like. Stat, Proportion Stats, one sample, Power/sample size. We want to click on the confidence interval width. So its default setting is to open up to the hypothesis test power, which is something that we may or may not talk about in chapter 10. We probably won't talk about it in chapter 10. It's an interesting concept, but there's only so much we can fit in the course, right? Anyway, what we want to look at though is the confidence interval width. So click on that tab, and then it should look like this. Now you're going to fill in all of this stuff with the appropriate information. So for example, when it says confidence level, if you read through the problem here, it tells us that it's asking what sample size should be obtained if she wishes the estimate to be within 4 percentage points with 90% confidence, right? So the confidence level is 90%. She wants to be within 4 percentage points. That's your margin of error, right? Margin of error is 0.04, which means that your width is 0.08, right? It's twice your margin of error. Okay, so we can enter those things, right? Confidence level, we want that to be 90%. Oh, I'm not sure if I should enter a decimal or a percentage. Let me see what the setting is. So stat, proportion stats, one sample, power sample size. Oh, it looks like a decimal. We should enter a decimal. So I'll say 90% as a decimal. The width, we said, we want the width to be 0.08. Okay. And the target proportion. The target proportion is the prior estimate, right? Whoops. So the target proportion is the prior estimate, in this case 55%. In part A, it's 55%. So target proportion is 55%. And then the sample size, I want to leave that blank. So hit compute. And there you go, right? It fills in the sample size that you need. So the sample size here is 419. Okay, and that's that, right? We used a prior estimate p hat of 0.55. Okay, and we got 419. Now part B says what sample size should be obtained if she does not use any prior estimates. So we're going to do the same thing, right? We're going to go stat, proportion stats, one sample, power sample size, 90% confidence level, 0.04 margin of error. But this time, our prior estimate, she doesn't have one, right? And if there's no prior estimate for P, then we just use 0.5. Okay, we just use 0.5. Because this is going to maximize our sample size, right? So the sample size that we need is going to be the largest whenever we use an estimate of 0.5. So we're going to do the same thing, except that p hat is going to be 0.5 here. Let's see what we get. So I'm going to delete that again. I'm going to say I want the target proportion to be 0.5. That got changed. I'm going to change it to 0.08 again. What happened? 0.5. There we go. 0.5. So we get 424. 424. Okay, so when you don't have any prior information, then you need a little bit more information in order to get the estimate that you need, right? You need a little bit larger sample size. This difference between this and that is going to be even more pronounced whenever your prior estimate is further away from 50%. But anyway, that's how you would do that. So call it a day there, and we'll see you in 9.2.